Well, all right. Let's get started slowly. I see the people still joining our session in person. I have no idea how many of you joined us online here because I don't see this number, I don't see this session. But hopefully my colleagues, which are on the back channel here, Christopher Ducker's a colleague of mine. Chris, just say hi. Yeah. And the colleagues that you can see right here still, those who watch online, you can see Alexander Prokopchuk, who is my co-host today. Alexander, say hi.
Hi, everyone.
Oh, that means we need to reduce the volume. We also have our colleague and co-founder, Basil, and Marcus.
Hello.
Yeah. Okay, all right. Marcus, say hi. Yeah, that's fine if you cannot. He's probably busy. Basil, can you check the sound once again, say hi?
Hello.
Okay, perfect.
Okay.
All right. Okay, we have my colleagues right here, and we are almost ready to depart. So first of all, let me congratulate ourselves and everyone for this amazing workshop. We worked really hard to make this thing possible for the first time in the industry. I mean, the GPU audio technology that works real-time, low latency, that is scalable, that provides you with consistent latency and work with buffers in multiple channels and multiple instances from multiple ways you can integrate that technology. That was a huge thing that required a lot of investment of venture capital, years of my life, and life of my colleagues, as you can hear.
Yes,
that's
exactly.
Special.
Not only
special.
yours.
So let me spend like 5 minutes before we start explaining to you how big it is. So we honestly started integrating NAM project 3 weeks ago. I had zero idea what is this about. Like, I heard there's a neural amp modeler. I know Stephen Atkinson, I believe he joined us online. So hello, Stephen. Thank you for everything that you brought to the community. We appreciate it very much. I had zero idea before. I don't know how it works, generally. I do, but like in code and how exactly it's been implemented, I have no idea until, like, I had no idea 3 weeks ago. And for our team, it took only 3 weeks to turn this thing on for real-time inference on the GPUs, okay? That says something. And we managed to make it work for Windows NVIDIA that will be showcasing after the presentation using my laptop locally. And we will be streaming this thing, the results online. This also works for Windows AMD. This also works for M-Silicon Apple. I'm not sure about audio unit, whether we built audio units or not yet, but after the presentation, when it will be publicly available, we'll make sure that we provide you with the audio unit as well. This thing, let me be mini me today, mini me Jensen Huang. So this thing should work on embedded GPU, which is NVIDIA Jetson, which I believe most people are interested in. I couldn't manage this work on this particular unit because of Chinese people that don't like to update their Ubuntu. And I couldn't manage it all because the manufacturer, the provider, they didn't provide me with the right binaries. I tried to flash it multiple times, but I failed. But this thing's supposed to be working. And I know there's another guy, and I'm very excited about it, that there are more people appearing every single year and sharing their own experience working with GPUs. There's another guy that was at ADCX gathering, Simon Schneider, if I'm not mistaken, who managed to bring on-next stack on the NVIDIA Jetson, and he was able to run at some latency. Not sure, I believe it was not like 1 millisecond, nothing like that, and there was only one instance, and he also mentioned the possible dropouts, etc., like problems he couldn't solve, which is absolutely normal. And this thing is capable of running whatever the neural network you want to bring of any type. And you can do way more that neural DSP is doing today using their ARM Cortex CPUs. And this thing could be as low as like $50 if you order a lot of those things. So call NVIDIA, not me. Yeah, I'm very much excited. Okay, I guess we're all set, and we can get started. Alexander, say something.
Yes.
All right.
Can you hear me?
Yes. So we will be reading through the presentation together. And after we read through the presentation and just get you acquainted with our SDK, we will dive into the Jupyter notebook, the cloud version of our SDK, where you can just watch the code work and you can just practice with that yourself. Okay, Alexander. So I believe this is part where you begin the presentation.
So, hello everyone. So let's start with a quick overview of the product that we will be actually discussing today, which is NeuralAmp Modeler. So NeuralAmp Modeler is the open source deep learning guitar amp and guitar pedal modeler. And it is available as a VST3 and audio unit plugin for both Mac and Windows. And it is also available as a standalone app for this for those platforms. So Alex, I'm actually not seeing the presentation, so I hope it is on the first slide of the presentation, right?
Yes.
Yeah. Okay, so here you can see the homepage of the NeuralAmp Modeler, and NeuralAmp Modeler was brought to us by Stephen Atkinson. So, giving a little bit of context about the guitar amps and their respective modeling, guitar amp, as you probably know, is a highly nonlinear device, and the emulation of those devices with conventional modeling methods is complicated, and mostly due to nonlinearities, I would say. And another problem is that for each particular amp, for each particular device and model, usually you have to design the model from scratch, which makes it a good fit for a machine learning approach when if you will pull out the right design, then you can basically do the rest by just creating the correct model for the correct device. And the NeuralAmp Modeler captures amp with the specific settings, with the specific knob positions, so to say. And this is why on the interface of the NeuralAmp Modeler, you cannot see the gain knob, because the gain knob will vastly change how the device actually changes the sound in the nonlinear way. So Alex, please bring the next slide. Okay, so here we have a quick overview, top-level DSP scheme of NeuralAmp Modeler. So from the plugin input, we are going to the gain staging, as most of our guitars are passive devices with pickups. We want to start with improving our signal-to-noise ratio. Oh no, sorry, the first will be the gain staging, right? The noise gate will happen after that. So the gain staging is a rather interesting thing. So because we are modeling the physical device, when the model was trained, it was fed with signals of a particular level. And inside the device, it was kind of physical measures of voltages and of the electric current. And when we are feeding the digital signal to our plugin, to our emulation, it's just basically some arbitrary float number between -1 and 1. All right, so when using the model, we should be correctly feeding the level of the signal that the model actually expects. So this is why the first thing that we do is gain staging. We should be inputting the signal at the level that the model expects. Right after that, we go with the noise gate trigger to improve our signal to noise ratio. After that, we go to the num core, and the num core is actually the part where all the be discussing today mostly. This is actually the module that we ported to GPU. This is what actually calculates and models the guitar RAM. After that, we have another noise cancellation module. After that, we have so-called tone stack. Tone stack is just a free band EQ, free band equalizer that you do after the modeling to basically shape the sound to your desire. After that, you have the model where you can load an optional cabinet IR, cabinet impulse response. It is optional because it all depends on how the model was trained and what we are modeling. Because if the model that we were training consisted both of the amp and of the cabinet, you wouldn't need an additional cabinet IR because everything will be in the model itself. And if the model represents just the amp, if you at least once heard how the raw sound from the guitar amplifier sounds to you, we will always want to apply a cabinet IR after that. After that, we have a simple direct current blocker. This is basically a high-pass filter. And then we just have the knob to control the output gain to match our needs. So Alex, please, we can go to the next slide. Yeah, thank you. So yes, before jumping into the details of today's main theme to the num core, let me give you a quick overview of the GPU Audio SDK. So our main goal is to empower our partners and tech-savvy audio developers to run audio processing algorithms on the GPU. And to this end, we offer an SDK that supports various platforms and is tuned for high performance and low latency processing. In terms of platforms, our support matrix is quite vast. In terms of OS, operating system, we support Linux, Mac, and Windows. In terms of GPUs, we support NVIDIA, AMD, and M Silicon. And in terms of CPU, we, of course, support x86, and we support M Silicon. And as Alex T already mentioned, we are already working on supporting the ARM and NVIDIA combination to be able to utilize devices like NVIDIA Jetson.
So I would like to add and extend what Sasha was saying about the platforms that we support. So as of today, everything that Sasha says, it is already cross-platform supported. So it's already there. But there are definitely more vendors of the platforms, including GPU platforms, including Intel. As you know, Intel could be there, but the market is not there, right? And that means when it comes to the laptops and desktops, there are not so many GPUs that sold to the people, right? So that doesn't make too much of the practical sense to support the platform for us and probably for you guys. But things are changing. We hope that Intel will persist and they will release more GPUs. The Intel Arc GPU, which is embedded GPUs, which is pretty much everywhere, this becomes more or less decent GPUs. So we want at some point support this GPU, but it's not there yet. But we have some plans. And as Sasha started mentioning that we are going to bring the ARM toolchain working for NVIDIA GPUs, but also ARM stack goes for other directions, right? So all the mobile platforms and embedded platforms like Qualcomm and Qualcomm Snapdragon, it's also ARM-based. It's ARM-based for host side, which is CPU side, as well as GPU side, Adreno. And typically you support those GPUs through OpenCL or OpenCL style, let's say, SYCL framework to enable whatever you want to do there. We are somewhat close to support Qualcomm. I'm not promising to bring Qualcomm tomorrow, but if there is anyone who is interested to bring something really big on embedded or mobile, we can cook something really quick within like a month or two. I mean, we already have something to enable this support, but we don't have, let's say, a partner that needs that. So if this partner is here on this session, let us know. Sasha, let me mute myself. Yay, okay.
Yes, thank you, Alex. This is 100% true. So if you think about, for example, if we are discussing this now about the NVIDIA Jetson, for the host side, we are already building our code for ARM architecture because we are supporting M Silicon, and we, of course, are building our device code, and we are supporting NVIDIA and CUDA. And we also support Linux, but for example, we do not have yet this combination because we had no clients to have Linux, NVIDIA, and ARM. So let me continue then. Our entire programming stack, both on CPU and GPU, is centered around C++, as it forms a common denominator, so to say, for all GPU-related programming languages. For the GPU, this means that we are running in a CUDA for NVIDIA, in HAP for AMD, or in Metal for M Silicon environment. And compilation happens through the native compilers. So, for example, for NVIDIA CUDA, it would be in VCC. We abstract all vendor-specific functions and map them to most fitting low-level functions when going through the specific compilation paths. We will talk more about this later today. I will show you the thing that is called simplified context to give you an idea what are we talking about. But basically, it means that as our code is multi-vendor, we can use something like __ sync threads directly from CUDA because every platform has its own primitives, and we provide an abstraction layer on top of that. So you can compile exactly the same code for different devices from the different vendors. While the code that you will write for GPU audio platform or on top of GPU platform, GPU audio platform is similar to CUDA and Metal. It is to some degree, as I've said, the common denominator of both, requiring you to limit yourself to the C++ language features that the Metal compiler accepts. So quickly, one example from the top of my head, that currently Metal compiler doesn't have support for lambdas. And exactly because of this, if you want to target all of the platforms that we support, you will need to use the visitor pattern instead of doing lambdas. It's an inconvenience, but sadly, it is what it is. However, if you do not want to target Apple Silicon, you can actually make full use of CUDA. That's also up to you. So depending on the functionality you need, we offer various forms of integration and already pre-built building blocks for you to directly use. And what I want to also say is that typical audio processing tasks only use a fraction of the modern GPU, actually. And this can open multiple scenarios for you as a client of GPU audio, as a user of GPU audio. Because one thing that can be done is that you can run really a large and vast amount of parallel independent tasks of the single GPU. Hundreds and thousands of tracks with multiple processors in your DAW or something like that. The other thing, then again, that Alex T already mentioned, that you can use embedded hardware to process audio on the GPU as well. And of course, one application scenario that many people consider right away is neural networks, because obviously GPUs are very well suited for this use case. So let me quickly walk you through the top level GPU audio components. So the first one is the GPU audio engine itself. It contains first and foremost, the very core of our technology. It is a low latency scheduler. So why do we need a low latency scheduler? Because when you're working with GPU, you may think of it as if you would try to run something on your CPU without having operating system kernel primitives. So you have no processes, you have no threads, you have no paging of memory and stuff like that. So in case you need to run many tasks at the same time, you will need to write a basically operating system kernel itself. For many tasks on the GPU, however, this is not the issue, because generally many use cases, so the GPU just assume that there is nothing running on the same GPU at the same time. So I don't know, you run a game or you train a model on your GPU and it just allocates all resources it can get. However, when we are talking about the audio processing, typical audio processing, for example, imagine running your DAW and every plugin here is powered by the GPU. So you will have dozens and hundreds of tasks to run at the same time. So this is why we need the low latency scheduler. When then the GPU audio platform basically has two APIs for you to talk with it. One is the engine API, and the other one is processor API. The engine API is the API that you use to integrate your product, your application with the GPU audio. And the processor API is the API for the engine to understand your processor. So you will need to kind of do two integrations here. You need to integrate to be the client through the engine API, and then you will need to run a processor, which can be then scheduled and executed through the processor API. And another thing that we are working on is the DSP components library. Well, I guess this part is pretty self-explanatory. We have an assortment of pre-built modules, various. Today, for example, we will be talking about delay lines for the ring buffer. We have FFTs, We have things to build neural networks, matrix multiplications, obviously, infinite impulse response filters, convolutions, finite impulse response filters, and a lot more. Yes, Alex, I think we can go further. Thank you. As I've already mentioned, we support many platforms, but today we will work in a virtual Linux NVIDIA environment. But the code that you will see can be exactly the same code, can be compiled and run on Windows and Mac, on NVIDIA, on AMD, on Apple Silicon, you name it. And in general, we distinguish between the CPU code and GPU code. Dependent on which platform we are running on, we also need different CPU libraries to work with the corresponding GPU. Yeah. I think let's go to the next slide, Alex. Yes. So here is the main concepts from the GPU audio that you will need to understand. First one we already discussed, it's GPU audio, which provides you the scheduler, the memory management, the graph setup and validation, and graph launcher. What graph launcher is? Basically, graph launcher is something that groups graphs that can be executed and processed to the specific GPU device. As you can have multiple graph launchers, you can actually utilize more than one GPU. And currently, we are mostly working in process, but we previously had an in-house demo of the IPC, and those graph launchers can actually be out of process, utilizing APC on or even over the local network. Then you can write your own load balancer, so to say, on top of those graph launchers and utilize, I don't know, dozens GPUs for some hard processing scenario. So then we have the processing graph. The processing graph, well, I guess it's pretty self-explanatory. At ADC 2023, I believe we were talking about processing chains, which were exactly what you see in the DAW of your favorite DAW. But later on, for many use cases, we decided that chains are actually too limiting for us. So instead of chains of tasks and processors, we now are implementing direct acyclic graphs of the processors. So you can basically do an arbitrary routing of the signal between the processor, as long as you, of course, do not create cycles. And then we have the processor. Processor is basically a node in the processing graph itself. And the process between the processing graph and processor, we have input ports, which allow us to connect the output of one processor to input to another processor. We have parameter passing control. Parameters is basically what you call parameters in your VST3 plugin. So it's your knobs, faders, and all that stuff. Yes, Alex, please, next slide. Quick info about the processor API. So the processor API, the processor itself is just a dynamic library. So example, it will be a DLL on Windows. And apart from the module class is actually representing the whole processor type module itself. Then from there, we have module info provider, which allows us to access some information that is needed for the platform to actually work with this processor. We have dynamic library interface, and we have a device code provider. The thing is that this module, this dynamic library, can actually have multiple device binaries inside of it. So we need a manager to get the correct device code for the device that is currently being used in the specific graph launcher. Next slide. Okay, and here we can see actually the port factory, which is used for creating the ports for this particular processor. We have the memory manager, because of course we need to pass some data from the CPU to the GPU, then we need to copy the result back. Then to do this efficiently on the host side, we need to use so-called pinned CPU memory, which I will talk a little bit about later on. The next slide. So yeah, now we will return actually to neural AMP modeler and neural AMP modeler. We will talk about the models that are implemented in the product itself. So the first one, the first model that is implemented inside them is so-called ConvNet, and it is a simple multi-layer perception setup that uses multiple layers that work on the current and previous input to produce new output. And being the first model, it's rather compute intensive. It is quite limited in how closely it can represent the desired effects. The second is the long short-term memory model, which is built around the LSTM cell, which has functionality to either use some more recent or some older input to combine with the current input. The model is more efficient than the ConvNet implementation, as it specifically models history and keeps the state around. However, the most recent and current model used is the Wavenet model. Being the latest and most powerful model, we want to replicate its implementation today. So today, in the code that we will be discussing, only Wavenet, the third one, is implemented. The core of the model is a dilated convolution to propagate information for the time domain. We completely base our implementation on the open source Wavenet implementation and just using our building blocks to replace the neural network operations to enable the execution on the GPU. Sorry. The models are completely identical, and we do not retrain the model or anything similar. So essentially, you can.
Sorry. Yeah, you can finish your sentence and then I will add.
Yes, what I wanted to say is that basically our goal was to just run the CPU and GPU model one by one and get exactly the same result. That was our aim.
Yeah. So as you can see, the difference between our approach and like typical machine learning approach is that most engineers work on the Python level, right? So they work with, let's say, Torch library or any other ONNX that then is binded and linked to the backend implementation that works with the GPU. Mostly it was used for only training the models, right? So you have a backend, as a backend, you have Triton C or TensorRT or something like that, right? And when you have this whole stack running, crazy Python, then TensorRT and all these things together, it's super hard to deliver you a consistent latency, especially when it comes to real-time audio, which is golden standard, 96 kilohertz, 1 millisecond, right? So that's why we want to go to the Python world, but after we make something work on the C++ level. So essentially, for us and for you guys to implement this whole thing, we needed to re-implement, let's say, TensorRT in our own way, because TensorRT clearly is closed library, no open source code, nothing there, as well as the TensorRT doesn't utilize the benefit of our software scheduler that does all of this magic of allowing you to work with tiny latencies, allowing you to scale your whatever you want to run, hundreds or thousands of micro tasks, graph, multiple instances from any environment, whether it's a DAW environment or game or whatever else you want. So this was the only way to do that for now. Okay, let's go ahead.
Okay, Alex, you can switch to the next slide, actually. Thank you. So what is the dilated convolution, which is the core building block of the Wavenet? The Wavenet architecture has been published in a paper by Aaron van den Oort. You can see the reference here in the slide. I believe it was in 2016, and by now the paper has been cited more than 1,800 times, which is quite a lot, sorry, to be frank. And the cool thing about this model is that it takes raw input samples and also delivers raw input samples. What it means that this model works 100% in the time domain. So there is no FFT, nothing like that. And another cool thing about this model is that if you will look at the graph here in the slide for those dilated convolution layers, is that you can have a very good data locality without accessing too much historic data at the single level. And as we will see in the code, this is very good for efficient computation on the GPU because you have good data locality. So let's go to the next slide. So this is the top level schematic of the NUM core. At the high level, we can consider that we work on a small buffer of input samples, for example, 32, 64, or 128. The current input data is pushed into the first Wavenet block, called layer array, and the output of the layer array may be pushed into another layer array, and so on and so on. And typically, for the use case of the NUM, there are typically 2 layer arrays. In addition, the current input is also forwarded to all layer arrays as an additional input. While the input for the NUM in general is a single channel, processing in the layer array may use an arbitrary number of channels, typically 16 or 8. So those channels are a part of the machine learning stuff, and they have nothing in common with the audio buffers and our audio DSP channels, so to say. For those who are familiar with the neural networks, these different channels can capture different features during dilated convolution. The NUM Wavenet calls the data that is moved through the layer array head, and there is always data being added on the top of the head. Okay, and now
I must say that the presentation doesn't look good because Google Slides love to crap things when converted from PDF. Sorry about that. But I just checked our presentation. Most of the presentation survived. So as you can see, some arrows here are not perfect. So sorry about that. But I think you can use your imagination to understand what's here. Sorry. Let's go.
Yes. So I believe there are 2 top arrows cluttered. So what they should mean is that you are getting unfiltered raw input into each layer array as well. So in each layer array, you have data input, head input, and the raw unmodified input. Yes, thank you, Alex, for the clarification. So yeah, now let's have a closer look at the layer array. The input and the head are first adjusted to match the channel count of the layer array and are pushed into the first layer. The adjusted input is simply called data in the model. The conv blocks here are 1x1 convolution blocks. We will later look in detail what this means, because this actually, again, this is the machine learning convolution, not our usual DSP convolution, so to say. Each layer also, but it is very similar in the most important thing, that it's also linear. Well, almost, because there is a bias, but we will get to that. Each layer also gets the original input and output data and head, which is moved from the layer to layer. Finally, the head output of the first layer is forwarded to the next layer array. Let's go to the next slide. So, and here in the layer itself, we can see where all the magic is actually happening. So the data is moved into the dilated convolution. The dilated convolution is exactly the diagram from the paper that we've seen previously. While the CPU-num model uses a matrix that is reinitialized during overflow, we use one of our common building blocks, a simple ring buffer that is usually used to implement the delay lines. So in order to, for convolution to access the historic data, we are just using the history ring buffer, basically. The input data is first stored in the ring buffer, and then we read from the ring buffer to perform the dilated convolution. In a typical setup, we read 3 times from the history, but any number would be accessible and possible there. The delays are different for each layer and can be dynamically configured. The read data is subject to a convolution, and it is again 1x1 convolution in neural network terms, and all results are combined. Yes, and here after the 1x1 convolution, we have the so-called activation block. What activation block is? This is actually the step where we introduce nonlinearity. And I believe that for the most, if not all, models that we've seen, the actual function, nonlinear function that is being used there is hyperbolic tangent. And the output of this step is subject to another convolution to form the data output. Yes, Alex, we can go to the next slide. So how we will implement this model on the GPU today? We will use 3 building blocks: a multi-channel delay line to implement the ring buffer. We will use the conv 1x1 operation, which is used almost everywhere, and we will actually directly use our matrix multiplication operations too, well, and of course the activation non-linear function. Okay, the next slide. The multi-channel delay line uses a ring buffer where we simply wrap around in the buffer after reaching the end at any end. And the size of the ring buffer must be sufficiently large to support the history lookup. Otherwise, the buffer wraps around before the history is actually read. And in this implementation, we enforce the size to be a power of 2, which allows us efficient wraparound in terms of unsigned in data types, efficient modulo operations, and things like that. It's very easy to work with addresses when your length is a power of 2. And finally, the ring buffer allows loaded store operations both as a vector. So if you, because this is a multi-channel delay line, if you are loading or storing a vector, you're actually getting a single sample for each channel. And also it supports a loading and storing a matrix. Then you will have multiple samples for each channel. The next slide. So, yeah, of course, matrix multiplication is the core of the most neural network operation. And matrix multiplication are typically computed by multiple threads together. Most often they are computed via warp, and warp is a single instruction, multiple data groups of threads, but also they can also be computed by an entire block of threads which will consist of multiple warps. And then matrix multiplication mostly is limited to memory access nowadays. Yes, so when we are multiplying matrices, it might be surprising to you or might not be surprising to you, but we are not actually limited by the operations themselves, multiplications and additions, but we are limited by memory transfers, which we need to wait for the data to become available and then to store the result back. And here also I will briefly mention that matrices can be held in multiple types of memory because GPUs have a rather complex memory structure. At least I can mention the global memory. This is what you usually are seeing on the box of the GPU that you purchased. For example, 24 gigs of VRAM. This is the global memory. Then we have the shared memory, which is considerably faster than the global memory, but of course, it's much less in size. And then we have registers, which is even faster than the shared memory. Okay, matrix multiplication. So this is basically just a quick recap. I believe that everyone is familiar with how the matrix multiplication goes. I probably will just mention two things. That during our computation, memory allocation, and things like that, we can rely on the fact that matrices A and B will always share one dimension. In this particular case, it will be the K dimension. And also, I already mentioned, no, I didn't. So yes, and another thing that we do is that we can have an accumulation when our multiplication is actually stored on top of some existing matrix to, again, save the cycles, save the amount of time that we would need to load another matrix C in to perform this operation. Yes, we can get to the next slide, I believe. Yeah, so
hold on. Thanks to Google, where my spouse works at, we have this slide quietly crippled. So if you allow me, Sasha, you can read everything except the crippled part. I will just read it from my own version of the slides, which is right here in my palm. Okay?
Okay. Yes. So Convolution 1x1 is used in neural networks to combine data across different channels, but does not take information from the other dimensions. For audio samples, this means that we only consider data in different channels, but at the same time step. Note that for the dilated convolution, the temporal domains is covered by different delays in the time domain. And the side effect of the conv 1x1 is that the number of channels can potentially change, and every output channel is a linear combination of all input channels. And of course, this obviously sounds like a matrix operation. If we looked at a single sample in time across all channels, it would be a matrix vector multiplication. But if we look at the entire window, this turns out to be matrix multiplication. And the matrix that describes how to map the input channels to the output channel is called the weight matrix, which is part of the model. And as previously noted, we can also supply an additional accumulator to add on top, which is default to 0, but sometimes we do need it, and it is being used in num cores. So yes, this is used to add a so-called bias, also a very usual way in neural networks. And this is actually another source of nonlinearity apart from the activation function. Okay, let's move to the next slide.
Yeah, I would like to add that the crippled part of the slide that you don't see here in this presentation, but you'll see afterward, the temporary shared memory provided by the class to load the matrix multiplication. This should be here, and input data either is in shared memory or in fragments or registers shall be stored. Let's go to the next slide. I hate Google.
Yes, and I will talk about this a little bit later when we will be viewing the code itself, why it is so. So yes, let's move to the... So yeah, in the next slide, you just have a quick recap that shows that conv 1x1 actually maps to the operation of matrix multiplication plus adding the bias that we just discussed. And we can move to the next slide right away. Yeah, so here you can see the definitions of the device processor for the processor step and things like that. Every GPU processor only needs an init method and can have an arbitrary number of process functions. There are keywords to annotate functions and pointers. This is the part that I previously briefly mentioned about the simple context and about the different vendors having different decorators for pointers, how you should decorate shared memory, how you should decorate registers and things like that. Because we are supporting all of them, we use our own decorators, which depending on the platform then are by the compiler converted to the ones that CUDA understands or Apple Metal understands, and so on and so forth. And in every processor method, you have the following additional parameters. Of course, you have the parameters themselves. This is your knobs and faders in the GUI in the interface. You have task parameters. I don't believe we will be talking much about the tasks today because the processor we will be talking about actually consists of one task. But I can just quickly mention that if you have rather complex processor, it might be that for the different parts of the processing, you want to allocate a different amount of resources. I mean memory, both global and shared, and, for example, threads. And in this case, you might want to split your processor into a few tasks. And this will allow scheduler to make its execution even more efficient. Yes, I believe we can move to the next slide. So yeah, here you can see some infographics about the performance on NVIDIA RTX 4090. So on the X, we are having the amount of tracks, and on the Y, we have time in milliseconds, execution time. So basically, as you can see, and as the one would expect, this doesn't grow linearly. So for executing one track at a time, we only spend 250, well, 1/4 of the millisecond, so to say. No, 1/4 of the second, sorry, to process 96,000 samples. And when we are processing 128 tracks, so basically this is by 2 order of magnitudes, a bigger load. The processing time only increases by 4.
Yeah, I would love to provide a little bit more context. So typically, the way you think about the SIMD devices, how they do operate real time, you expect from these systems that whenever you add the payload, you don't expect the execution time increasing, right? So that's the exact reason why we don't mention just like one buffer and the execution latency, because it doesn't make too much of sense. And the way you should think about what GPUs, NPUs, massively parallel systems offer you is not who is faster. This is like the 3rd year I'm giving a speech at ADC, I think 3rd, yes. When I say it's not about who is faster. CPUs will be then faster if you want to run something really small, just because they have direct access to the memory rather than any PCI Express based device, right? So GPUs are all about to give you a huge, almost limitless resource that you can use for something else to bring some new cool feature or new functionality that neither CPU or DSP or FPGA can give you. So that's the reason why we say, okay, if there is like a huge buffer over the time, which is huge, I mean, huge 96,000 samples, right? That we process real time in chunks. Let's say by chunks 64 samples, let's say at 96 kilohertz, right? So we have only execution time without the dropouts of 0.66 millisecond, right? So this graph also represents how much of the payload you can do whenever you process this amount of buffer by chunks real time, and how it depends the payload and how the execution times depend one on each other. In ideal system, the execution time should never grow, right? But in real systems, it should grow very, very slightly. If there is no parallelization or no parallel implementation, every single doubling number of tracks shall lead to a double amount of execution time, which is not something that you can see here, right? So as Sasha already mentioned, Alexander already mentioned that processing one track and processing 64 tracks, it just almost triples the execution time, right? So we managing to run 64 more of the payload within just execution time 3 times more than that, right? So rest assured, if you just do a very simple calculation, divide a few numbers, one on each other, you will quickly find out that processing the NUM core takes on average 0.16 millisecond. So yeah, that's numbers for RTX 4090S. Super. I'm not sure. I need to ask Marcus. Marcus, just let me know, is it plain or super version of the 4090. Okay, it's super. Okay, cool. Thank you, Marcus. Let's go ahead for the other numbers. Alexander?
Yes, we can go to the next slide. So, yeah, here you can see some big picture about the saturation. So if we are running 128 tracks of processing with NUM with buffer size of 64 and processing 96,000 samples, so for example, for a 96K sampling rate, it would be 1 second worth of sound. It already takes 10 seconds to process. So we are way oversaturated, and we are way past the real time. And when using GPU, we are still real time in this scenario. So the plot that you see on the right is just slightly zoomed in because otherwise you wouldn't be able to exactly see the GPU numbers because of how long it takes for the CPU to process this. So yeah. Then we have some performance metrics for MAC-M2. As you can see here, again, for the different amount of tracks, how much time it takes to execute. And I believe those are GPU-only statistics. The next one is the average call latency. Again, how it goes up with the amount of tracks increased for different buffer sizes on the GPU. And then...
Yes, and the importance of this particular slide for Apple, as some of you guys already know, because Apple M-Silicon laptop systems, this is what? A single GPU device, right? And it has shared memory. So it's a different kind of architecture, different, in some ways, even programming model. And that's why it's important, because it's like one single device that holds it all, including operating system, GUI, Chrome, all that crap. And latency is way more harder to tight consistently, so to say. In my RTX 4090-based Razer Blade, whatever, $4,000 super expensive laptop, I have Intel GPU as well. So I can do a little bit of tricks and use my Intel GPU to render everything else. And my NVIDIA CUDA device could be available for whatever real-time audio compute I want to do. As you can see, that's pretty much different case, right? And a different in whole stack, starting with hardware scheduler of the GPU device, going to up driver, and the way driver works for specifically operating system, Windows, and for macOS, and so on and so forth. So it also already took into that account. Surely NVIDIA are the best in terms of latency, and they're the best on Windows, which you may wonder actually. Windows probably the best operating system so far today for that purpose. But these guys, again, Jensen Huang moment, this thing, because it runs Ubuntu, and because you can even do a custom kernel if you want, you can go, I don't know, like the lowest latency we have in our platform system is 50 microseconds. This latency is available at scale. So whenever you run, let's say, cascade of filters or any other DSP components or neural building blocks, you would be able to run a bunch of those, like tens or even hundreds, within super tight latencies. That's really important to mention. Go ahead, Alexander.
Yes, thank you. And then, yes, you can show the last slide with the performance info. This is the graph which represents the conditions again on MAC-M2 Max for the different configurations, and for all of them, you can see that we are still in the real-time boundaries. Okay, Alex, we had a question, and I have this question for you also, because this workshop is quite large. It's 3 hours long. Maybe we should get a 5 to 10 minute break until we dive into the code. What do you think?
I agree, and I think people agree. So for online participants, yes, that was not the workshop yet. We exactly, for those that have their own timing, you can just go to the ADC 2024, use these credentials to sign up, and after you signed up, create another credentials that you'll use to sign in because Linux sucks, and the servers, the web servers that work for Linux sucks, and then you can have access to Jupyter Notebook and start learning yourself using our slides, as well as just start exploring stuff. And we will get back just in 10 minutes. Right. That's like the best way to provide you the similar experience, guys. So this is, yeah, 1 second. This is a Jupyter Notebook, so you will be able to build something for NVIDIA GPUs on Linux servers in the cloud, and you would be able to run something there. The performance test will not be as you can expect on local systems, but we will cover it after the break. And there are some questions here before the break. Yeah, go ahead.
Should I think about?
I think yes. I think yes. You can use microphone. Yeah.
Okay. Yeah, thank you for this workshop or this talk. I wanted to ask, you always showed only average execution times.
Yeah.
So how are your experience with the variation in these times? Because they are very important for real-time audio programming.
Yeah.
Do you have some standard deviations or maybe some numbers, how these differ?
Yeah, so we don't have this on these slides, but I can just tell you. So the difference between the direct native way, let's say using CUDA SDK and evaluate latency and consistency, if you run a large kernel or you run something bigger than empty kernel, you will end up quickly with a percentile or hit of your latencies that go in for, let's say, 5 milliseconds to 20 milliseconds, so it's inconsistent. Our stuff, you would be able, right after this workshop, you would be able to see this thing operating from my local laptop using ISO for all, and you can watch yourself how this works consistently. And also, Marcus has his own answer for that, that I need to read from the chat. Give me just one moment. Just one moment. Hold on. Yep, on Google Meet.
One quick note for me that for the use cases with the NUM that we tested in the Windows environment that I tested personally, for 100 tracks, we had exactly 0 buffers going over 1 millisecond.
Yes.
So it was completely 100% real time.
Yes, so no dropouts, nothing you can expect. So that's why we don't put any charts like deviation, and that we don't make this happen. Like, it doesn't make sense. If it doesn't work, then why we organize the entire workshop? So the way we represent those charts is for you to understand that we anyways complete all of the processing on time. So it's 100% hit within the buffer latency. And this chart just explains to you how much of the processing's DSP components you can dispatch at the device. Because the other alternative approach, let's say Simon Schneider, that represents his own way to run the NUM model, or another guy who will be given, I guess, a workshop that is dedicated to neural synthesizer. They just use the out-of-the-box CUDA implementation where you can run some functions, some tasks within, let's say, 3 to 5 milliseconds, but then it goes inconsistently. And therefore, they provide you with the charts where you basically see how many dropouts could be happening, or what is the percentile, what is the hit of missed buffers. I mean, the real-time processing factor. We always guarantee that. We always guarantee that. What's more important, after the workshop, when I'll be running this on Reaper, I'll still host Google Meet, Chrome open. I can even run something on Steam, and this will work. You can see this yourself. There was one more question. I hope I answered. Thank you.
You showed the call latency, but you didn't show the transfer latency. Is this somehow?
Yeah, so I think I got the question. So this is the third year I presenting GPU audio stuff. And the bias of the community exists, like GPUs are slow, persists on the fact that people don't read PCI Express standard. The standard says, starting with PCI Express 3.0, that you can pack, let's say, 64 megabits per half a millisecond latency, and every single standard, this amount of the data you can pack within this curvature of latency against bandwidth increases like quadruples, right? And you can be absolutely safe that anything you want to pack on the GPU with real-time latency, you can do that. Like, because in audio, there's like tiny pieces of data, right? 96 kilohertz, 1 millisecond, 96 samples, floats. You can pack doubles if you want. The typical data transfer latency goes microseconds, even nanoseconds. It just depends how quickly you want to make a response, right? And you don't need to make a response in 1 microsecond. It just practically doesn't make any sense. People's ear work with latencies 0.1, 0.3 millisecond when you can distinguish the latency, right? It doesn't make any sense to go below than that. The golden standard in the Pro Audio was always 1 millisecond latency at 96 kilohertz, right? Like, if you go below, well, yeah, maybe some people will notice, but most no. So our system can go round trip plus running stuff at scale and going back, all of it within 30 to 50 microseconds, as I mentioned, right? So this is crazy. The scheduler, the low latency software scheduler, which is our patented technology, it is settled by default by 200 microsecond pulses to the device. Within those pulses, you can just update whatever you want to do on the device, including all of the data transfers, including all of the graph metadata, including all of the launch dispatches, if anything changed, so it's like damn fast. All right.
Yes.
So let us have a free time for offline participants that are here, and I will read through the questions, online questions I received. So, and Alex, you can also read them, or you can have a break if you want. So, the first question was, do you have any Mac, Apple Silicon CPU versus GPU performance benchmarks? Marcus replies that not right now, but can be provided a bit later. And there was one question for particularly this slide, which I believe it's not really important, but I still would like to answer. Sorry about that. Google Slides are not good for that thing. Yeah, the question was, what is head in the block diagram? And head is the naming used in the NAM model. It's essentially an accumulator that is added on top in the layer array, which then becomes the output of the layer array. And let me see. Okay, so this is question maybe for you, Alexander. If you're online, just turn on the camera. If not, we will take this question afterwards. You're online. Okay, so as you can read this question, Alexander, in our Google Meet. It says, could you provide a small instruction on which Jupyter Notebook file precisely entails the demo. I'm constantly hitting empty Jupyter Notebook files for whatever the reason. Yeah.
Well, we will actually be running in the console, so there will be no IPython-B files. There will be just some bash scripts to compile, run some demo, and I will go through the code with you.
Perfect. So if anyone from the audience also want to ask questions in this break, feel free, go ahead too. Or you just use your time to sign up, log in to the Jupyter Notebook. And I'll have just a 2 minutes break from now on. Thank you. So there's one more question that I think really important.
Okay. Yeah, I was just, I was trying during the talk to have a feel for the difference between running the AMP modeler. So within the AMP modeler application, what would be the difference in latency or in performance in general between running it on, say, the Mac versus running it in neural DSP, quad cortex, or some kind of other benchmark on something quote more standard or something, whatever that means.
Yeah, thank you. So as I was already mentioning about the latency, because the whole system already works with the minimal practical latency at 30-50 microseconds. This is the lowest that we can hit data transfer on the device, running something at scale, let's say like dummy tasks or pretty lightweight tasks, plus returning back to the context of your program. This is 30-50 microseconds, so this is damn fast. You don't practically need that much of low latency in your world, right? I also mentioned that the entire system works with pulses by default of 0.2 millisecond, 200 microseconds, right? This is our scheduler, software scheduler pulses device with parameters of the processors, with data, audio data, with the meta information used to run the graphs. That means if you change the logic of your program through the, let's say, graphic user interface, you could expect this reacting as fast as 200 microseconds, right? It's damn fast. And it's regardless on the operating system, hardware system, driver stack, whatever. It works as fast as these latencies I mentioned. Practically, you don't need those latencies. Practically, the golden standard that we took as a golden standard is 96 kilohertz, 1 millisecond, 96 samples. This is like, we guarantee you whatever the system you will use at the end, Mac, Windows, Linux, whatever GPUs you will use, whatever anything you will use, you'll always get things on time and even faster than on time. That includes everything in your call stack. You can go as low as 0.2 millisecond, which is the pulse, to receive it faster if you really need it. But I don't know, if you want, let's say, I could imagine the case that for Mac, for Apple, you want to complete computations on the GPU within 200 microseconds, and then have, let's say, 0.6 millisecond to do whatever you want else on the CPU side and on the GPU side. You can also have that. And it's not different neither for Mac, neither for any other setups.
Basically, yes, but the thing is that if you can go faster, you can also accumulate more processing. At the moment on a Mac,
yes,
if you open a series of plugins, you say you want to do live mixing on a Mac,
yes,
you're going to kind of break the kind of
sure,
latency pretty quickly. So if that is an avenue for being able to do, for example, live mixing on laptops, I'd rather be convinced about it.
yes,
to be honest. So
okay.
yeah.
Thank you. Yes, so think of it 0.2 millisecond, the fastest thing that you can have by default, and you can have plenty of time to complete whatever you do for your application, product, service, wherever you use GPU deployed at. This could be embedded devices, that could be based in cloud, this could be just a software application running locally on a user machine, whatever. So when we created this whole thing, the platform, we were thinking big, because otherwise our investors will not provide money, honestly. And we wanted to cover it all wherever the audio is. And today, and it just happened that historically at ADC, we were targeting the hardest use cases, which is the DAW, because the DAW, the VST3 interface, I just hate it personally. I have a lot of hate against VST3 because it's still not asynchronous. It is synchronous, wasting CPU cycles, doing nothing when we do the workload on the GPU. And it still shows some CPU cycles wasted purely. That's why I hate this interface. And the point is, the Pro audio use case is the hardest one because they have lowest latency. Whenever you deal, let's say, with games, right? And you want to, let's say, integrate something into Unreal Engine or Unity, you can just use our engine and call it as a DLL library, offload any shit you want, like, I don't know, you want to do sound propagation, right? And in this sound propagation graph, you want to render the portals, the scene, plus you want to run some filters, you want to add something on the top. This absolutely the same way you use this platform, absolutely the same way. And you build it and target different operating systems using the same unified API. So when we were thinking big, we were actually thinking about all of the use cases possible. And by the time when it will be available for mobile platforms, it will be absolutely the same way of utilization. Right. I guess 10 minutes passed, Alexander, and you can probably share your Jupyter notebook and
yes,
go ahead.
Just a moment.
Yeah, and I'll just shut up and have your screen share running. There are more questions, Alexander, so let's talk about questions as well. Yeah, go ahead. I'm sorry.
Yeah, sorry. There was a challenge getting signed in a few minutes ago. I just got signed in here. You said something earlier about creating new credentials once we get into the notebook.
Yes, so I mentioned that use these credentials to sign up. And when you are signing up, create another credentials to sign in, and then new credentials used to sign in and log into the Jupyter notebook.
Yeah, thank you, Alex. So, yes, let's start from the quick overview of what is actually here in the workshop available to you. So, in the root of the workshop content, you should see some scripts. Basically, the first thing that you want to do is to execute a build.sh script to build the binaries of the processor and the numlib. On your part,
excuse me, Sasha. It will be very useful if you always name the file that you're switching to, because people probably cannot read the name of the files from the presentation. So what is the current source file you're at?
Well, I'm not on the source file. I'm at the I'm in the console. So you can just hit the plus button here, then open the terminal, and then you can launch the build.sh script.
Perfect.
To actually run the build. On your part, it will take considerably more time than on mine because I've already built my binaries prior to the presentation, but it should compile them after some time. Then the next script that you will have here is run tests, which will just run the unit tests over the engine and the processor to check if everything works correctly, if the GPU output is the same as the CPU one, and things like that. And of course, we are in the virtual environment, and we are stressing, all of us, the same CPU and GPU, so the performance will be not as good. Yes. After that, there is another script here, which is called process samples. Basically, in the root folder of the workshop, you have two sample wave files, ADC sample 1 and ADC sample 2. And if you will look into this run samples, process samples, sorry, a script, you will see that it just launches the num-process file to terminal application. It supplies the model and the file to process, and then writes the output to the another file. And due to the fonts, I'm very sorry, here it fixed. And it will write the output files right here, and using right-click, you can actually download those files and listen to them. You can download the raw samples also. Then you can do something like bring and upload your own files here and things like that. Okay. So this is basically the scripts to show you and be able to run something. Now to the code and the binaries that we are providing. First of all, let's quickly discuss the GPU audio bin folder. This is the folder, this is the directory where the binaries of the GPU audio platform itself is being held. So all the binaries, like external NVIDIA test, GPU audio NVIDIA test, they shouldn't consider, we shouldn't consider them today. They were just today for me when I was preparing the workshop to make sure that all the unit tests are passing and everything works as it should.
Yeah, Sasha, do you also want to add that the binaries of the platform for Mac or for any other platform will be added afterwards, right? For those who want to build for anything else, or provided afterwards, right?
Yes, we will provide it afterwards, but I will speak at the end about this. So let's focus on the workshop for now. And other things that we are having here, again, leap clock dummy processor is something that we should not consider today. It's just a simple processor which outputs the unprocessed sound which we use in the unit tests. Then we have leap GPU audio NVIDIA dynamic library, which is the engine itself. And then after your compilation will succeed, you will here also notice the libnum processor NVIDIA, which is the processor of neural amp modeler compiled specifically for Linux NVIDIA. And then let's begin talking about the code. So we have two directories here, numlib and numprocessor. Before, during the presentation, I have mentioned that GPU audio engine makes two interfaces that are available to you, the engine API and the processor API. And that's exactly why basically we have two separate building blocks here. Numlib is being used to connect the actual VST3 audio unit or whatever plugin or standalone application that you have to the GPU audio platform, and numprocessor is the processor itself. So let's have a look at the numlib. In the numlib, we will, well, let's actually start. Let me. Yeah, I'm sorry, because the fonts are so big for you to be able to see what I'm showing. It's really hard for me to navigate when I'm seeing only 10 lines of code. Yeah.
That's fine. Go ahead.
Yeah. So here we have a top level component which is being integrated into the plugin. We can see here the executor config, which defines the number of audio channels that we will be passing as inputs and outputs of this module. We also always are setting the max samples per channel, so the maximum buffer length that we are using for the particular instance of the processor, because this allows us for more efficient memory management to know in advance how large the buffer can get. And later on, here is just some infrastructural stuff. When we are getting the instance of the GPU audio engine, we are querying a device info provider to get the actual GPU that we are working on. Then we are executing the graph launcher that I've mentioned earlier today, and the graph launcher actually is already tied to a specific GPU device that it will launch us the graphs. And then we are creating the processing graph, and we are adding a NUM processor to it. And that's about it. The source in the NUM folder, this is actually...
Can you mention where exactly we alter?
Yes, I'm just getting to that. So yeah, the sources in the NUM folder, this is actually almost unmodified source of the NUM core, of the original NUM core by Stephen Atkinson. The only thing that we did, now let me quickly find it, is here. So the plugin uses the get DSP function. The NUM plugin uses the get DSP function. It provides the data of the model, and then it gets out the object that will actually do the processing. And here you can see that if the architecture is equal to Wavenet, and if the used GPU flag was supplied, this is actually the only thing that we had, almost the only thing that we need to modify here at this used GPU flag. And if GPU is being used, instead of making the CPU Wavenet object, we are making our own GPU neural lamp modeler. And that's about it with the integration. And now we can go back to the root and proceed with more interesting stuff in the actual NUM processor. Let's go to the NUM processor, and so in the include we have only one struct specified, which is needed to be shared between numlib and NUM processor, which actually specifies these max buffer samples and the data that will be passed to the processor. Mostly this is the model itself. model itself. So it's the weights for the head scale, for the dilated convolution dilations, and the weights themselves. Then let's go back to the source. And in the source, basically, we have directly some files here, and we also have the device directory. Why is that? You can think of it that the files that are inside the NUM processor SRC, this is what we call host code. So it means that this is a code which will be compiled for the CPU platform, and for example, in this case, it will be compiled by the GCC, or to be precise, with G++. And in the device folder, we have the code that will be compute for the device, so for the GPU, and in this case, this code will be compiled by the NVCC. And then you can see that there is quite a lot of files. I will not go into the detail about all of them, because things like NUM module library, they are basically, this is just some infrastructural stuff to define the version of the processor, to define the version of the contract of the processor API that this processor supports, and things like that. Then I guess the only file that we should look at the host side is the NUM processor CPP itself. And let us start with the constructor. So in the constructor, we are getting the processor specification and the module as the input parameter, owning module of this processor instance. And we are setting some things up. So we are setting our output port. We are telling that this port will be regular port, which means that it will contain float samples. We define the sample type as 32-bit float number. Then we define the capacity. And also we define the interesting thing called grain. Here you can think of it as a level of data parallelism. This is how many samples we will be processing in parallel, so to say.
Yes, I will introduce some comments here. So this is probably the most interesting thing, because we use just one thing right here, right now implementing is a Wavenet based, and probably one more. Just let's say a Wavenet-based processor, we know what it's made of. We know the degree of the parallelism of the algorithm itself. But you can define as low as you need, depending on which DSP components you use. And as an example, we use some of the, in our DSP building blocks, we use some of the components that require less than 32 threads. And if you are anyhow familiar with CUDA, it has a minimal number of threads. You need to synchronize them using the barrier is 32. Why it's so important? Some of the filters may require just 4 threads or 8 threads, right? So if you will just end up coding some of the product that will use, let's say, filters with 8 threads, you still using CUDA will utilize 32 threads, but most of those threads will be just wasted. They will be doing nothing. And if you're familiar, again, with CUDA or anything else, there's a term, occupancy. Occupancy basically tells you if you have a high occupancy, you greatly occupy resources of the GPUs to do the useful compute. And in the case when you actually use 8 threads to compute your DSP building block, like your filter, you waste 75% of the warp just like that. When you run these DSP components at scale, let's say you run them in parallel across multiple channels, you also have this occupancy factor 25%. So you're wasting your GPU allo cores that are distributed over multi-processors of your GPU, right? And the same goes if you implement any hybrid DSP scheme when you, let's say, have some of the components of the filters, like second-order sections, made in parallel, right, in the channels. But you also have something goes after in a sequence, right? And if you don't manage this thing, or you use native frameworks, you will quickly end up in a situation when you're allocating all of the resources or a lot of resources on the GPU, yet you do a very little of the useful work. And you will wonder, why the hell I cannot run like 10 instances of, I don't know, NAM plugin or whatever using my freaking RTX 4090. That's exactly the reason. That's one of the exact reasons why you should be using GPU audio instead of going native, because neither SYCL, CUDA, OpenCL will provide you this way to have greater occupancy. Neither they will provide you with DSP building blocks that has higher degree of the parallelism already inherent in the implementations. This is very simple project where you have only one processor, you do only one thing, you just define 32 and go on. You do all perfectly. When you will build really complex products, you will quickly end up in a situation that I tried to run like a few kernels and this just simply won't work. GPUs are latent. No, that's one of the reasons why it happens. Sasha, go ahead.
Yes, thank you. Another thing that we can see here is that in our input port, we are setting the M transfer to CPU to false. Why is that? Well, because if you have the complex graph with many connected processors, the need may arise to get some data out of the processor in the middle of the processing chain or processing graph, to be precise. You may imagine it like you are passing the output signal of the plugin to another plugin, but you want to get its output, for example, to use it in a side chain for a compressor on a different thread, or you can want to have some data sent to your GUI to, for example, animate the level meters or spectrograph or something like this. And GPU audio also has ability to do this, and you can use the callback system and transfer data back to CPU from anywhere in the graph. Okay, let me quickly see what else can we discuss on the host side, on the CPU side. So there is a setup function which gets the numconfig specification. Then it allocates pinned CPU memory on for the Wavenet. This is also a very important thing. So for those of you who might be unfamiliar with the concept of pinned memory and what this is, to be able to efficiently transfer data between CPU and GPU via PCI Express, the best method is to use pinned memory. You can think of it that the pages that are being pinned in the CPU memory kernel will not physically reallocate them. And because of that, they can be very efficiently transferred to the GPU. And that is why we also always used pin memory for the data transfer in such cases. And later on, we are just constructing the Wavenet, we are setting the head scale, we are setting the weights, we are setting the dilutions, and preparing everything that should go into the GPU for it to be able to actually do this. And then we are using the GPU audio platform memory management. We are copying the resulting data, which now resides in the pinned memory, to the GPU. Okay, this is setup method, receive data transfer. Yes, rebuild tasks. In this case, there is nothing specific happen because is happening because all of the processor is defined as a single task. The only interesting thing that you can see that here we are explicitly specifying the amount of shared memory that we will allocate for this processor, as well as the size of the parameters, the thread count. So basically, this structure holds how much of the resources we will allocate for this task to be able to process different kinds of memory, threads, every resource that you have on your GPU. And I believe that for the host side, it's more or less it, because all other things will be pretty familiar to you with from working with Juicy or VST3. Things like prepare for process, they have rather similar meaning. And now we can dive into more interesting part, into the device code. Into the device code. So let me start probably with the simplified context. So here you can actually see what was mentioned by me and Alex T earlier. This is exactly the abstraction layer, which provides you the platform agnostic primitives for working with GPU and its resources. So identifying the current thread, which block it is, which thread it is, ability to synchronize the thread in the same warp, and so on and so forth. Getting your shared memory pointers, getting offset in your shared memory allocation, and so on and so forth. This is what we actually provide, and later on in the processor code itself, you will see that we are not using, for example, CUDA-specific underscore sync threads or something like that. We are using this simplified context everywhere.
Let's wait for Alexander, and I can just share a little bit more information about, he will jump back really soon. So the context, as Alex mentioned, it's a cross-platform implementation. So on the device side, this is the same way you will be coding the processor for everything. And we don't provide too many primitives for you there compared to CUDA, what offers by CUDA or OpenCL, just to be in focus what minimum you should be supporting in your code in order to implement the processing part itself. Alexander, are you here with us? Can you unmute yourself?
Yes.
Perfect.
Yes. Can you hear me? Can you
I was telling some
view
jokes.
my screen?
I was telling some jokes. Okay, let's go.
Okay. So then after viewing the simplified context, let us go into the top level of the Wavenet. So as we've seen in the slides, the Wavenet consists of the layer arrays. In all the models for the neural lamp model, what we've seen, they all use exactly 2 layer arrays. And of course, actually, this struct could be implemented in the more generic way with arbitrary number of layer arrays using variadic templates. But for the workshop, we just wanted to make it more simple and at least to some degree understandable. That's why we just hard-coded it to the 2 layer arrays. So yes, you can see that we have layer array 0, we have layer array 1, as well as the head scale. The interesting part here, I believe, is the structure of the shared memory. So we have the input matrix, and then we have a union for the layer array 0 temp and layer array 1 temp. This is done in such a way to minimize the amount of shared memory that we are using, because layer arrays are being computation through them is being executed one after the other. We actually never need 2 of them at the same time. And because in theory, the size, the actual size that we need for processing the first layer array and the second array are different. As far as I know now, they are not, but this could be the case. We are using the union. But in any case, at the given point of time, we only need only one of them. And here we are defining this explicitly, so to say. Okay, now from the Wavenet with 2 layer arrays, we can go and look what is layer array build of. So here we have the rechannel conf 1 time 1, we have head rechannel conf 1 time 1, and again we have a structure which defines how we are using the shared memory. And here is the process function. So here, I believe, yes. So first thing that we do is that we rechannel the input, because as was seen in the diagrams, well, the input and the output of the NAM is always mono, but the layer arrays and layers have multiple channels. So we need to distribute the data from the input. And then we are just passing the data through the layers themselves one by one. As you can see, we have pragma role here because num layers is basically more or less, I believe it should be even known at compile time. So compiler should be able to completely remove this loop from the actual code and just copy paste the process call with the amount of layers that we have in the current layer array. And here we are passing data, we are passing condition. Condition is the naming for the unchanged input. So in each layer and each layer array, we are, on top of everything else, we are passing the unchanged input, and it is called condition. We also pass head input, then the layer temp, and of course the ring buffer cursor for the internal ring buffers of the layers themselves. And each layer will change data and it will change head. And then it will pass them through to the next layer. After we have gone through each layer, we are again rechanneling with the head. Yes, another thing that I forgot to mention here is the way that we are working with the matrices. So as you can see here, the first thing that we do is that we are loading our input matrix into the shared memory from the global memory. And after that, we do context synchronize. Why is that? Basically, what load limited does is it will work no matter how the amount of threads is corresponding to the amount of samples that we need to actually process. It will figure out the workload itself, and then, as you may know, in the GPU, the two main things that you should be always concerned about is the occupancy and divergency. And if, when loading data, some of the threads were idle, so to say, and they did not have the data to copy from because the buffer was smaller than the amount of threads that we allocated, we explicitly need to synchronize all the threads, and for those threads to wait for the others to finish this. And immediately after this, what we are doing is that we are then loading the matrix from the shared memory to the registers. It is done in such a way that a matrix is distributed. So each, so to say, that each group of thread will have its own matrix fragment that it will work on. And as the registers are the most efficient memory on GPU, it is very important that we do so. And of course, at the end here, you can basically see the process which goes in another direction, writing the output out.
If I may add, so as you guys see, those who follow the code, those who follow the presentation, there are steps particularly, right, in the comments. And if you compare the original core code that implements this processing block implementation, the Wavenet itself, that's not much any difference at all. We just use very few functions to work with mostly with data. We put them in the ring buffer, we load some special stuff in the shared memory, and this a little bit more additional calls. And anytime we process anything, we synchronize threads, that's it. Like the way to migrate your CPU code to the GPU one is quite straightforward. It is also, for those who are anyhow familiar with CUDA or any other framework, it's absolutely the same. It's just use our own namings, and we actually hide a lot of the pain from you to deal with just programming the device side function and just manage very few things in the context and so on. Like it doesn't require you any special knowledge if you are aware already what the CUDA is about, and it doesn't require you too much of the infrastructure code to be put. in order to make it work for multiple platforms that we support. Go ahead, Alexander.
Yes. Thank you. Again, just to give some context, when we were discussing layer arrays, and that there are usually two of them in the models used in NUM. Usually, the first layer array has 16 layers, and the second one has 8 layers. And then let us look at the layer itself. After we looked at the layer array, let us look at the layer itself. So in the layer, we have quite a long type depth for the dilated convolution itself, for the ring buffer, for the input mixin, and for the output 1x1 convolution. Well, actually, input mixin is also a 1x1 convolution. And then again, we have the structure of our shared memory, and in this case, we have one union, so at given point in time, we only need one of the 3 of those variables. We have the matrix fragment, so the one that will be stored in the registers, and we have input condition, which is basically, as I've mentioned previously, it is an altered input, so basically we defined it as a matrix, but actually this is 1 times num samples matrix, so it's a vector. Okay, now let's talk about, let's look at the process function. So, yes, we prepare this, we prepare the ring buffer. Then we will form something called zfrag. This is original naming from NEM, and because we were just basically implementing this one-to-one, I am not even quite sure what this naming is. Please forgive me. And we are doing the dilated convolution here, using our ring buffer, the data, the temp, and of course the cursor, after which again we need to synchronize our threads. After that, we are doing the mixing conv 1x1 convolution and adding the unaltered input on top of the zfrag that we got from the dilated convolution. And after that, we are performing the activation using the visitor pattern. As I've mentioned previously, due to the Apple Metal limitations, we can't use lambdas, so we used visitor pattern instead. And basically what activation does, it just applies the hyperbolic tangent, introducing obviously nonlinearity element-wise, or the whole zfrag matrix. Then we are forming the head, adding the zfrag on top of it right after the activation, and then again we have to synchronize our threads, and then we are doing the 1x1 convolution on our output.
Just basically following the DSP schematics diagram. That's straightforward.
Yes, yes, yes. I think that if you will afterwards look at the diagram and at the code side by side, you will quickly, you can quickly basically make the match between them, between the different built-in blocks. Okay, now let's look at the dilated convolution itself, which happens in each layer. We again have quite long type def for the fragment of the matrix. What we will be storing in the registers. We have matrix shared, and we have the bias that will be added on top where it is enabled. We again have the process function. Where we initialize the accumulator from the column vector, and then again using the kernel size, how many times we should actually look into the history. We are looking into the history, and for each step, of course, we are using the dilation, which is set up for the current layer. And after that, we are just multiplying two matrices and store them in the accumulator, which we then return. What else can we look at? So, for example, one thing that we can quickly look at is the implementations for the matrix and matrix operations themselves. If you will look at this code, it is quite low level. Then again, there are multiple implementations because there are matrices stored in shared memory. There are matrices stored in the registers. Basically, yeah, sadly, with the font size that I'm currently having, it's completely unreadable. And well, I just want to say that this is the reason why you need GPU audio. We will provide those building blocks for you. You will have your matrix operators and can build anything you want on top of them. And this part will be on us.
Yeah, so the reason why I love so much about it, it's basically a PyTorch plus TensorRT behind, but put right here in the very quick way. As we say, we also ship our building blocks library, which is one of the ways we distribute it through this workshop is neural building blocks, and we just re-implemented linear algebra methods, very basic ones, and some tensors as well. For DSP library, we provide more filters like IR type of the filter that is, by classic design, is inherently sequential, right? You need to find alternative approach how to implement this type of the filter on the system such as GPU. So that's another reason why you don't want to deal with CUDA, because CUDA offers 0 of those. Even if you do some like TensorRT, well, yes, but you'll quickly end up with running just a few on a huge, very expensive GPU, a few of whatever you want to run on the GPU. Yeah, so basically this matrix, just a few moments, Sasha, this matrix source code is the exact building blocks that you can then reuse and to build your own neural network, whatever, made of those building blocks. And you can extend this neural amp model to something else. And you can alter this and you can just compile it, build it, and then there you go. You can reuse the same interface, but I don't know, replace the Wavenet with something else. That's pretty much it. Alexander?
Yes. Thank you. So another thing that we have here is, of course, the conv 1x1 implementation, which uses the matrices. So this is what we already been discussed in the slides, that we multiply two matrices, and if the bias is provided and is set to true in template parameters, we apply a bias on top of that. Another thing that we can look at is the activation functions, and basically in all the models that we've been using for testing, this one was used. You can see this visitor pattern, and that we just element-wise are applying the fast implementations of hyperbolic tangent. So I believe in terms of the code itself, it is more or less it. So once again, let me return to the console. As I've said, to try it yourself, first of all, you will need to run the build script to build everything for you. And then you can do a process samples and download the files and listen to them by yourself. You can try to upload your own wave files into the workshop. You can try to maybe you can try to tinker with the code and to understand it in more detail, then getting back to the presentation to gather some additional details. So what are our plans to the future? Basically, I must say that the platform itself is now pretty mature. We have LTS interfaces internally that we are planning to provide the backward compatibility. And for now, we are facing only one challenge that we still need to solve before we can provide everything that we showed to you just on GitHub as plain source, and then you can compile it on your own machines for your Mac, for your Windows, and experiment it however you want. There is only one challenge that we need to solve. Basically, our target architecture is a Cartesian product of CPU architecture times GPU architecture times operating system, and it becomes quite a lot. On top of that, we have different version of compilers, we have different version of CUDA, we have different version of HAP, of Metal, etc., etc. Internally in our company, we have quite vast CI/CD system, which does all of that for us, but we will need to find a way how to provide at least part of this to you, to be able to build this for the platforms that you mean and want to target, because there are quite a lot of limitations. For example, you can't compile Mac code if you don't have Mac, because there is no basically cross compilation, and Mac completely disallows any kind of virtualization. Then just to mention, current amount of target profiles that we are using internally when everything is multiplied: CPU architecture, GPU architecture, operating system, various CUDA versions, compiler versions, OS SDK versions, is 300, which is quite a lot of profiles to be built on CI. But that's our support matrix. We can do nothing about it. So our next step is the public release of our SDK preview. Please stay tuned.
Let's spend some time for Q&A session. And there you go, the way you can port neural amp modeler from just open source straight code to our platform. For us, it took 3 weeks. We were not quite understanding much what we were doing in terms of machine learning. Like in general, we do understand, but we didn't know about the project itself right before we picked it up. So it took only 3 weeks. I think it's marvelous that we we ourselves to manage it within a certain amount of time. This SDK will be available, Sasha, hopefully in January, something like that, which is
yes, hopefully January 2025.
Yeah, so you would be able to download all that thing. This will be the very first thing that we will share with the community. As Alex mentioned, you can alter this. For those who wonder, like, okay, I want to get into the bandwagon and I want to start today, you can always be in touch with us and just write to me, Alexander at GPU Audio, or just hello GPU Audio, and request for SDK that we can ship privately for you. The reason why we don't ship publicly, didn't distribute this, and don't distribute it still, because as Sasha mentioned, it takes 300 configurations to support, and we understand once it is public, everyone will write about everything. And we simply cannot manage it all. We don't want to ruin our reputation and relationship with the developers. That's why we hold it privately. We already have some companies that we've been dealing with, smaller, bigger, and so on. We ship the SDK. We implement it for someone, for one of these companies. You already know VSL. MIR Pro 3D runs on the GPU. We reduce CPU usage up to 10 times. We already showcased this during the NAMM show, which is in Los Angeles, previous ADC and so on. We also work with audio modeling, brilliant guys. We already shipped the processor to them. I guess it just on their side when the product will be available. For another company called Mantra, among those that we already shared our projects with, they already have a demo build that we are going to showcase tomorrow at our booth, so please come in. You would be able to see 64 channels mixed, combined together with high order ambisonics, like I think 5th order ambisonics. This is kind of a product itself, a category itself of the product, a spatial reverb that you probably never experienced before. And this also works locally, real-time, latency, and so on and so forth. And yeah, I'm here for your questions as well as online part of the audience. Feel free to ask questions related to this particular workshop and our platform. And then I will be demoing, I will fire up Reaper, and I will be demoing the GPU version of the NAMM plugin. Anyone?
Question online.
There's one. I don't see. Which one?
Shall I take the mic? Shall I do it on the mic?
Sure. Go ahead. And feel free to take a microphone from Christopher afterwards, those who attending in person.
Okay. Yeah, can you say anything about what kind of license terms will be attached to this for commercial releases? Even a ballpark idea.
Yeah, this is probably the hardest question for us. So we are a commercial company, we're a startup, venture capital backed. That means that we need to return money, right? And as you can see, this is quite a lot of innovation done here and quite a lot of engineering time spent to just make it possible for you guys as well. So for those 3 companies, we have a kind of revenue sharing model. So they didn't pay a dime to make their own products GPU powered. We just provided SDK, they integrated, then we agreed all the products that been sold to final customers and users. We have our own margin from each copy being sold. So as you can see, it is as flexible as it could be, right? And we don't take any money upfront. There could be some models depending on which type of the business you run. Let's say you run, I don't know, a cloud-based service with subscription. This could be a different type of the monetization, but we prefer to work with whatever works for you and don't take money upfront. There are larger enterprises that want to build absolutely something new and GPUs are the best device to do so. With these companies, we work in the way we run pilot projects. We provide the SDK, surely, first. We run some pilot project. We see whether it works or not. And then once it is almost ready to be shipped, we can charge per license depending on the volume, how many licenses the partner think will be selling during the year. Let's say 100,000 license, and the end price will be like $500. Well, we can have as less than 100, so to say, or even like 25. It really depends on the model, and we are not greedy, as you can imagine. We are not taking anything like tenths or half of what you guys want to earn. Our business model is just to provide you the way GPUs can be unlocked. And as you can imagine, it goes way, way, way beyond what was considered under the CUDA or any other native implementation. It goes to mathematical implementation of building blocks. It goes to the multiple platforms. It goes to the what I call undocumented code behavior, where the other people, Simon Schneider that I mentioned, and I forgot the name of the guy who will be presenting neural synthesizer, mentioned that latencies are inconsistent, or you cannot run too many instances real time. You cannot make it run in, let's say, under Unreal Engine and so on and so forth. This thing provides it all.
Yes, Alex, let me quickly add on top of that. So regarding the public SDK release itself, of course, the GPU audio platform, I guess it always will be closed source. And as for the code that you've seen today, we will provide the full this full code to you. And in regards to the SDK itself, we are planning to do double licensing in a similar fashion like Juicy does. So as long as you stay open source, you can do whatever you want with it. If you want to use it commercially, you will need to acquire a commercial license.
Yes, perfect. Thank you, Alexander.
Yeah, I had a question about, obviously your scheduler is part of the closed source, so I'm not going to ask you details, but I'm curious if your early implementations attempted to use like an existing cross-platform API like Vulkan, and whether or not it did, what were your challenges? Like, what prompted you to realize that like we need a scheduler to like access that level of latency?
Yeah, that's a perfect question. Don't start another company in the audio, please, as I'm going to share some of the level of the detail. So we have this guy, Markus Steinberger, who is our co-founder, a really brilliant guy, and you can just check his own papers. He's actually probably former or maybe present professor at Technical University Graz. The guy won Best Paper Award at ACM, if it says something. And back then, back in 2017, when I was failing together with Sasha Prokopchuk and my partner and co-founder Basil, failing to build what is now considered by GPU audio, I realized we need some kind of ray tracer or rendering engine, right? And that was the times almost before PCI Express 4.0 and after PCI Express 3.0. And I noticed that there are good examples that you can run, like Async API and then later on Graph API. They allow you to do so, like run some kernels really quick with low latencies, but then afterwards everything crippled, and you don't know why. You just basically use like debuggers like NVIDIA Insight, and you see things going freaking wrong, but you do everything according to the documentation. As one great example of things going wrong is overlapping. So you know, in PCI Express, there are 16 streams going in and going out. If you don't do this in very specific way, even utilizing Graph API, which kind of guarantees you that you run things properly, you will see the launches not overlapped, which is crazy. That means the hardware scheduler puts it to run one after another. And this is the way you cripple all of the latency, you hear the dropouts. That's crazy shit. And like, when you deal even with the golden standard of the GPU, which is NVIDIA CUDA, it is always, even today in 2025, you have observable behavior, you have documented behavior, and you have real behavior. And it's happening because of the operating systems, drivers, CUDA stuff, your context of your application, and it's so hard to manage. So we understood we need like the way to guarantee these latencies. To provide this way, we split the scheduler on two basic things. One is device-side scheduler. So device-side scheduler, just make sure you run things on the device in the proper sequence, and you always have the data, including parameters, including audio buffers, everything. And by the way, the scheduler is abstract. It just runs, if you read our pattern, it runs just recursive and non-recursive algorithms for process time series data or whatever. So it can be used in telecom as well. And there's a host-side scheduler that just does very stupid thing, batches all the data together and pulses to the device. But the devil hides in the detail what exactly you run and how exactly you run. So basically, you want to prepare everything everywhere before you actually start the work. That's what we do. That's the explicit implementation of the scheduler. And the device side required you to do some stuff on the ISA level, which is assembly language level, to, let's say, implement sync threads. The very basic primitive, which is barrier synchronization for your threads, right? So in order to deal with the 4 threads degree of parallelism of your filter or whatever you write in your processor or component of the processor, right? In order to deal with some other weird shit you want to do, let's say cross-channel synchronization, which is a huge pain in the ass, to deal with, let's say, something that can be built as a compressor that has a side chain, and it's like extremely hard thing. And we've done all of it, so we guarantee ourselves that when we trigger the processing, everything happens on time. So CUDA and OpenCL has zero to offer you anything like that on the C++ high-level way, right? You can indeed use ISA level to implement anything you want, and you can override the behavior of the device without altering the behavior. Because the reason why so, because you have your own context of your application, right? So that guarantees you that anything you build, GPU audio or your own way audio stuff, and you make it run, will not interfere with pretty much everything you have on the GPU that already are allocated all the resources, shared memory, all that stuff. So yes, it is super hard. So you can still try like build using NVIDIA Jetson, because it's like dedicated device. It hides all of the implementation. You can run a kernel, like don't care about anything, run within 3 milliseconds, and you can implement your quad cortex neural DSP. You would be able to do so. But if you want to go beyond that, it would be impossible. I hope I answered this.
Yeah, thank you. Promise not to start another company in the space.
Yeah, sure. All right, let me see. Yeah, the online questions. We have like 10 minutes more, and then I should fire the demo.
Okay, so this is from Abelardo on Discord. I'd like to work with GPU audio in academics or academia. Can I use the SDK for that purpose? If so, what should be the procedure?
For academia purposes, all right. So you're a student or a PhD student, right? As I could imagine. Yes, so you can just write to us or wait until it goes public. Hopefully on January. We postponed this many times, but hopefully now January. And you can, as long as it's not commercial, something you want to produce and never be used for commercial purposes, you can do whatever you want for your own research. If your field of research is not about audio, but the way to run code of the GPU, by the way, I studied that thing. That's the reason why I started this company. then you can still collaborate with us. You can probably improve something, our internal scheduler, or you can improve and provide the better way to integrate our platform to pretty much anything else, right? So one of the great examples today, and the reason why I hate VST3 and audio unit, hopefully AX will be also changing soon, is because it's blocking synchronization used between the plugin and host. This is crazy. It's almost 2025. We waste CPU cycles whenever we deal with the external device, and we have to use the double buffering. This is crazy thing. Like, I understand the reason why it's still there persists, because the DOS, not all the DOS implement Graph API in their mixing engine, right? And the DOS are quite complicated, and there's a lot if-elses in the code that still people are lazy to replace. But if you can just implement the best way GPU code can be running, you can, for example, have 0 CPU cycles wasted whenever you need to offload anything on the GPU. For whatever there is in run machine learning, spatial audio, or I don't know, do some crazy things in 3D, which is possible as well. Yeah, you can do that with us. Just write us at hello@GPU Audio. Hey, Jan. Hello.
Hey, Sasha. Thanks for the presentation. So my question is, because we had a nice presentation of the code and how a particular model is implemented, and now comes January next year, and the SDK is released. But my feeling was, and I think I'm not alone in this, that it's not straightforward. Like, even with the abstraction layer that you provide,
yes.
Which I'm pretty sure, like, it's hard to simplify it even more.
Yes.
Then I feel it's still pretty complex to, write your own model, your own code. So I was just curious how you plan somehow to facilitate this experience of, new users coming to your platform, like in terms of, I know, documentation, tutorials, etc.
Yeah, perfect question. So there are two parts of the answer for this question. Number one is parallel programming is hard. So that's the reason why there are not so many people there, and that's the reason why audio community is not there like at all. And we understand the huge gap between high-performance computing, accelerated computing, that is now machine learning and graphics, and audio community. We used to process everything sequentially, right? We didn't care. But if you stick to it, you'll never innovate. You never, like, things that happening at Las Vegas Fair, my best examples that I usually refer to, like wavefront synthesis and beam steering, where you can recreate those audio objects in space, and you can like simulate virtually the Doppler effect. You can like hear and feel the sound propagation in the room. That's freaking crazy. These guys, they use FPGAs and huge server racks to mix more than 100,000 channels, right? Can you do that with CPU? Well, you can still, but it will require to break the bank, right? But you can do that on just a tiny GPU device, not like tiny, but yeah, like 96 gigabytes, like out of Lovelace, which is pretty much not expensive today, right? And you can scale from that huge experience downsize to, I don't know, like home speaker setup. So that's one part of the questions and answer. And the second part is, yes, we understand how parallel programming in general and math algorithms are hard. So that's why from the day one, we're providing ourselves with DSP building blocks, right? So this exact workshop will be the first release of our SDK, where we'll use the same materials and provide more guidelines on how to build this thing and how to alter this thing and do your homework. Let's say you want to replace Wavenet with other model, and you want to run more activation layers and do this high quality with the long tails, whatever you want to do for the guitar. The same we want to do, hopefully on a quarter basis, but I know Alexander now is scared. At least say half a year, where we want to provide you with the use cases and well-written recipes how to use platform for the particular ways. A year ago at ADC 2023, we gave you a workshop, Go Spatial with GPU Audio. That was a workshop we used to provide you on the code basis we used for VSL MIR Pro 3D Reverb plugin. And we are going to publish this thing right after this one, right? And we will be doing so, and we'll providing you with more cases and how to integrate this platform for the other environments, not just the DAW, let's say, to the Unreal Engine, right? Because it requires you to use ray tracer of Unreal Engine, right, to understand how sound propagates, and then to apply the processing, multi-channel, multi-rays, whatever. And let's say to provide the exact recipes on how to implement like DSP components or machine learning components to do the processing itself. Yes, that's our plan. And that's the reason why you shall give us money. I mean, whenever you release anything. Yeah. All right. Yeah, we have like 7 minutes. Yeah.
Hi, Ollie Larkin. I'm at Ableton and also maker of the iPlug2 plugin framework.
Can you speak louder? I'm almost half deaf.
Yeah, I'm Ollie Larkin. I work at Ableton. I'm just, yeah, thank you for the presentation. I just had a couple of points. If someone were to license your libraries and they send it out to loads of users on all sorts of different platforms with different kinds of GPUs, what kind of stack traces or what could we expect from a sort of maintenance point of view?
Oh yeah.
And maybe it's also related, but like if you're developing with these things, what kind of debugging capabilities are there?
That's an amazing question. Sasha, would you like to take it because you are most experienced with that?
Sorry, it was hard for me to hear the question.
I will tell you once again. So the question was, what if someone includes our platform and license our technology and use in their own software, and something goes wrong and we need to patch things on our end? What is the typical way to provide maintenance in that case? You can tell about VSL, how we deal with that, and how we plan to deal afterwards.
Yes. So basically, I think the main thing here is I was mentioning something like LTS interfaces, which we plan to support and make it backwards compatible. What this means that if we hit a certain sort block, a certain roadblock in a certain environment, in a certain product, what we can do is that we can issue a new version of GPU audio platform which works around this problem without breaking any other products. And then the product vendor can create a new installer with new version of the product, which will pack the new version of the engine with the issue fixed. And this will not break other products, and they still will be cross-compatible with each other. And our engine installers will work in a way that if the installers of a certain product sees that the GPU engine in the target environment is new, it does nothing. If it needs to update it, it will update it. In the that's one part of the answer. The other part of the answer regarding the the debugging and getting to the root of the problem, the usual thing. So it all starts probably with some ticket in the partner customer support system. And then if we need some additional data, I don't know, some crash dumps, or at least which GPU was used, which GPU driver was used, yada, 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 to know all the details of the environment, then we try to reproduce it on our end. And, well, it goes the usual support way.
Yeah, so as additional comment to that, we have like VSL users already complaining about some of the issues they face. Most of the issues they face comes from AMD drivers, really scary thing. We even scared of AMD drivers, but we love to work with AMD to provide you with the best experience. So the way it works for VSL, user submit a dump crash dump, sorry, and then they analyze whether it's on their end, or if it's not, then they forward it to us, and we just reproduce this bug and try to fix that on our way, on our end. And yes, as Sasha mentioned, the platform itself was, the concept of the platform was designed in that way that multiple vendors of GPU-powered software, as you see guys here, can run on the same user end, like a laptop, with different versions of the SDK you guys support, every single of you. Some have outdated SDK, some has latest SDK, and provides like continuing integration and updates, etc. We can run it all, we can load it all, we can like distinguish those things. And then as we provide our incremental updates, we fix some of the issues, and we say to our partners, GPU software vendors, like, we fixed these particular issues and just upgrade your stuff. Like normal way businesses do their daily work, so to say. And also this is another good point, is that whenever comes something new GPUs, believe me, you don't want to deal with that either, because they can introduce some new things and they can make things obsolete. Apple is the best representation of that. If you ever deal with Metal and macOS X version, you will quickly find out that they have a lot of hard dependencies, even in their own ecosystem. Apple, they have limitless money, and we deal with that for you. So whenever a new MacBook comes with the new stuff and some things go obsolete, we try to provide you the same very minimalistic, yet still hard wrap that you need to use to create your own applications. All right, maybe one more question before I hit the button. Any of you guys from the audience or online?
I did have a quick follow-up.
Yeah.
There's no one else. You were critical about several plugin APIs.
Yes.
Is there one that's good for what you need to do?
Well, we suppose we do our best. I understand why this problem of EST3 exists. They have a ton of the plugins released like for the entire 25 years or even more. And they have the Cartesian product of DOS and that stuff, and that's the reason why it still persists. But sometimes when I speak with the developers of those companies that establish standards, they are not even listening. And that's the reason why I have so much of hate. Like, guys, they are not interested in just enable a very few things, even for those who are open to bring it up. I hope that CLAP as a standard will actually implement asynchronous way to process blocks. And they will be the first, as well as Bitwig, who was originally the first DAW to support CLAP. And I wish we do that and collaborate that, because the others, they just don't listen. I talked to pretty much any DAW developer, and I said, like, at ADC 2023, we said we need like these 2 functions to operate in that way. And that way we can guarantee you can have very small CPU usage, which also is useful when you use your laptops with battery, right? And this is also useful in the case you don't want to have your fans spinning a lot. People like, that's the whole problem of the industry. The community in the audio industry is pretty much scattered. Everyone does its own damn narrow thing. That's why we encourage everyone to speak to us, to think open mind, and to try things to integrate. We provide like pretty much everything. If you are able to embed it, we will always ship you the best code possible.
Thanks very much.
Sure. Alexander.
Yes, I wanted to add on top of that. So the problem with the the problem with the synchronous interface of the process block and the VST3 in the audio unit and the others are, it's not a problem as long as you are doing everything on the same device, on the CPU. Then your DAW usually constructs amount of processing threads which is equal to your number of cores, and you can bottleneck your CPU pretty easily without any problem. However, if you are processing on a different device, and I think that in the near future it will be just inevitable. Look how many very different computational devices we are now having. We are having GPUs, we are having NPUs, we will have a lot of them because we kind of are at the roadblock where the Moore's law is actually no longer relevant, and so we need to optimize to push even more and more and more throughput, less latency, and so on and so forth. And if you are computing something not on the CPU, you immediately need a sync.
Yeah.
Because you don't want to waste cycles waiting. You just dispatch a task, provide the callback, and that's all.
We're actually volunteering for those guys who created mixing consoles, external synthesizers, anything at education that utilizes Raspberry Pi and things like that. All right, so we have not so much of time left, so let me be very quick. So this is Reaper. I'm still evaluating Reaper. I'm very sorry for many years. Hopefully, you guys will not evaluate GPU audio for that many years. So I use just to request sampler rate and request block size, which is eventually just 1 millisecond. And it doubles because we use double buffering because thanks Steinberg. And yeah. And I'm gonna switch hopefully seamlessly to my NVIDIA high definition stuff because I used to stream from, I just realized that I'm not sharing my screen with the online part of the audience. Yep. Boom. Yeah. Infinity mirror, right? Oh, I love Infinity. All right. So I, just for online audience, I switched, oh no, don't tell me so. I hope I tricked the 96 kilohertz because let me do that. And then let me go back and going back, 96 kilohertz. I hope this gonna work. I somehow tricked this last time. Okay. So as you can see, there are 13 neural amp modular instances right here. It's all default. I'm not gonna open them. I'm gonna just hit the playback button and hopefully this is gonna work. Can you up a little bit of the volume? And I hope that folks online, they hear it. So let me reset the graph. Boom. Okay. Does anyone hear the dropouts? I cannot. All right. So that was 13 instances. Let's go for duplicate. And let's go for duplicate once again, like, shit. Come on. Yeah, it's consistent. Any dropouts? So it's 40 instances. And let me see task manager. There should be somewhere the engine. Yeah. Yeah, it's running in the, I believe, it's running somewhere in the background. Yeah. And the Reaper itself, it utilizes for whatever there is in 20%, but in reality, it should be zeros because we don't do anything on our end. Let me add more. Let's say, let me just increase the latency a little bit. I don't know, like 256. Boom. And then let me add way more. I hope, let me just duplicate everything. Boom, it will take some time. Come on, Reaper. How many? 144. I'm not sure that's gonna work, but let's see. Yeah, I know why. I probably need to adjust the number of cores, right? Where is the course? Yep. Hold on. And let me see if I done that correctly. Well, hopefully it does. No. It's not, but I'm not sure what's wrong with my Reaper, but the project that I had made more. Maybe it's because of the camera. It's
144.
Yeah, well, no. What I'm saying is that, the console test that you can run and these charts that you can run, they are, I suppose, 128. In that, I just don't know which number shall we hit real time. Okay, yeah. So it's for RTX 4090, it's 128. Yeah, it's 128 the maximum. So maybe I need to remove not 144, but like 120 exactly. Yeah. Let me see, and that was for. Let me close it and open once again and see if I can manage like 64 or 96, right? Because I don't recall exactly how many we're supposed to run and what was the maximum number, but I suppose something closer to 128 or 120 without Chrome and all that thing running. And you have to understand this all goes as it is. The dose, call it as it is, 54. Let's add probably one more. This should work. Okay, I was not knowing how many. And we are streaming stuff using everything, everywhere, and HDMI of NVIDIA, GPU, etc. So believe me, everything matters. CUDA will not allow you to do anything like that. That's it. I hope you guys enjoyed.